Okay, so let's start the class. So we'll be discussing basic fundamentals of transistors. So we already have discussed one application, transistor as a switch. So we already discussed this transistor modeling as a switch is like just analogous to our mechanical switch. You give a pressure, it is on. So here the pressure is given you through voltage in the control terminal. Called this is the control terminal. No terminal, there's a base called an NPN transistor or PNP transistor. This is a control terminal. So it will be connecting the other two terminals, right? Say terminal one and terminal two is getting connected. Similarly, like in a switch, mechanical switch, where you pressure, you give some mechanical pressure to make the contacts connect together, right? So, so likewise, we have other applications of transistor like amplifier and like filtering operations. There are some other applications. So we'll be discussing briefly about those applications. So first of all, we should know the basic structure of transistor. It is we have a semiconductor, maybe silicon or germanium, and in that semiconductor we'll make different regions. Like we dove with n region in one part of semiconductor. So basically, first we'll take an n-type material. This is how this is constructed. We'll take an n-type material initially, then we put a small p-type doping in some small portion. That is p. Now it becomes NPN transistor, right? So if you make a PNP transistor, initially take a p-type silicon and you dope a small region of the p-type silicon. This is P, this is P with the n-type material. Right, this is the PNP transistor. Now, after this thing, we'll have to make slide connections, metal connections over this semiconductor. Right, so this is the way is done. Right, so this is one type of transistor. Okay, so we have three regions which we already discussed, I think, in brief. The first region of the transistor is called emitter, emitter region, emitter, right? And another region is called base region, base region. And the last region is called collector region, collector region, right? So this is similar in the case of PNP transistor also. There's a emitter region, there's a collector region, and there's a base region. Okay. So, and definitely there should be a metal structure which connects the voltage, which gives a voltage onto the semiconductor material. So it's metal. You can see the connectors, metal connectors. Okay. So, you can see this is a symmetrical structure. You can see in both ways, left and right. If you see is NPN, and from right to left is also NPN, and similar in the case of PNP. So is it a symmetrical structure? The answer is no. The transistor is not a symmetrical structure. Right. So you can even compare the transistor into combination of diodes. For example, you may see this is P and NP. So you can say, is it like this? Like diode P and N, and again a N and P. So is this connection, and there is three connections. Is it like that? We can do things like, and in same times NPN it will be so P and N. Again another diode P and N, and the top region is called P. So I'm asking one question. So this is same. The structure wise, this looks same. Structure wise, looks two connection back to back diodes connected together. So will it perform as a transistor if we connect two diodes back to back and have three terminals, one on the end and one on the middle of the connection? Will it work as a transistor? The answer is no. It will
No,
not work as a transistor. Yeah, you're right. Sandeep, you're right. So why? Why? Because there are some properties uh, which we try to utilize the in the working of a transistor. And this properties are something like the doping concentration, and there is the size of the different regions and their cumulative effect. The combination effects have different other effects which help the working of transistors. So we'll discuss what makes the transistor structure different, and this is not symmetrical actually. So although it looks symmetrical, materially wise, N, P, N, and P, and P, all both left and right same, but there is some difference in structure. So we'll just have a deeper look in the transistor structure. So one of the important things you have to see in it, let's take a N-type material, and we have doped a P-type material on it. So this is N, this is P, this is N. So here you want to see the dimension. You can see the emitter region. Uh, First, we'll look in the base region. Base region is the most thinnest region here. In the transistor, the base region is most smallest or the thinnest region, right? Then comes the emitter region. The emitter length is the largest. It is much larger than base, but it is more than the collector region. And collector also, they had dimension which is much more than the emitter region, right? Now this is about length and width of the size of the transistor. So length and width dimension, so called dimension. Now what about the doping concentration of the? According to doping, we have the maximum doping concentration or maximum doping is done on the emitter region E, right? Then the collector concentration is less than emitter concentration. That collector region will be lightly doped. Although both emitter and collector are n-type semiconductors, but the collector is lightly doped. Base is heavily doped. And what about emitter is heavily doped. And what about base region, which is a p-type material? As a base is also lightly doped, right? So now, now we have to discuss what are the different possibilities of uh, biasing the transistor. What is biasing? Biasing is give some input voltage to the transistor. That is called biasing, right? So let's discuss what are the different possibilities. I already told you we have to give some metal contacts to the semiconductor so that we can give some voltage to this different regions, right? So this is the emitter region, the base, and this is the collector region, right? So when we connect a voltage here, V, so this voltage will be across emitter and base. So this voltage across the emitter of a transistor and the base of transistor VEB. What about this voltage which is across the base and collector? This is VBC or VCB. Okay, this is the convention. And if there's a voltage across the emitter and collector, we can say VEC, right, or VCE, based on the terminal which we take initially and positive and whatever, right? So this is different terminology which we'll be using. So voltage across emitter and base VEB, voltage across base and collector VBC, voltage across emitter and collector VEC, right? Okay. Now, what are the how many possibilities of biasing is there? How many possibilities of biasing is there? Okay, first of all, we have discussed that emitter is heavily doped, base is lightly doped, and collector is not lightly doped. Collector is moderately doped. Right? That we have to understand. It's not the doping concentration of collector and emitter is somewhat similar, but emitter is emitter doping is somewhat higher. Right? So, so I can write like this: doping concentration. So emitter doping is greater than collector doping, and this combined doping is much greater than base doping. Something like this. You can draw something like this. So what's the meaning of this? Collector is very heavily doped in terms of concentration. For example, NPN transistor, N-type semiconductor has been doped very heavily. Collector is moderately doped, but somewhat lesser than emitter, and base is very lightly doped. Right. Now size. Based on size, we can again say emitter. So collector having the greater size, and emitter slightly less size, and much these are much greater compared to the size of the base region, right? So these two things I can just write like this. Okay, now I'll again tell you another thing, that three different operating regions of a transistor. So operation of a transistor, operation, operation, right? Of BJT. Let's focus BJT, operation of transistor. Here bipolar junction transistor. Okay, there are three main regions. Here, first region I call active region, active region. Then another region is cutoff region, and third region is saturation region. Saturation region, saturation region of a transistor. Right. These are very important. These are the most important questions. What are the different regions of operations? Although there are one more region that is not so important. So we will discuss definitely. Okay, so what are this active uh, cutoff and saturation rate? So we already drawn the transistor. So let me also draw the symbols of transistor. So this is the transistor. So I already discussed one day how to find the terminals, which type of transistor you're using. So you can see the arrow, the arrow. This is arrow denotes the current direction. So we know the current direction. Current always flows from the P to N region, right? So we have to know this is arrow is from P region to N region, right? So this is the last region will be N only, definitely. So this is an NPN transistor, right? So again, we have another type of transistor, something like this. So just see the arrow pointing, arrow point. So this is arrow pointing, and we know current always flow from a P to P region. This is N region. This is P region. So this is the PNP transistor. Okay. So this representation is important because will be connecting voltage, different possibilities of voltage across these three terminals. Okay. Now let's see some combination permutation. How many possibilities are there? Right. So we have NPN PNP transistor. So we have three terminals in the transistor. We have emitter. We have emitter region, base region, and collector region. And we have three types of biasing. We already two types of biasing. We know forward bias and reverse bias. So what is forward bias? We know in a diode, when a p-type region is higher voltage than an n-type region, right, is called forward bias, and reverse, it's called reverse bias, right? So this is the different biasing. So each of these three regions, emitter, base, collector, and even this is emitter base junction, this is emitter base junction, this is base collector junction, and we have one more possibility of giving voltage, emitter collector voltage junctions. Emitter collector can also be given some voltage. So you can see how many possibilities are there. So this emitter base can be forward bias or reverse bias, right? So likewise, each of these terminals can be forward bias or reverse bias. The two possibilities. Again, this also can be forward bias and reverse bias, right? It's very simple. So how many total possibilities will be there? Two possibilities. Each junction, there are two possibilities: emitter base collector, and emitter collector. So how many possibilities are in total? We already discussed in the principle of counting. If one thing can happen in n ways, another thing can happen in n ways. Both things can combinedly happen in m into n ways. So here are three events are there. One thing can happen in here two ways, emitter base collection in two ways, base collector junction in two ways, and emitter collector junction in two ways. What are the total? Yeah, eight possibilities. That is nothing but 2 power 3 or 2 into 2 into 2. There are eight different possibilities of operation. You can see biasing and transistor, right? So things are not simple. Diode we have very simple. There are two terminal device. So we have how many possibilities? Two possibilities, right? We can have forward. This is forward. If one thing is forward, higher voltage, and another thing is reverse. So only two possible. But here we have three junctions and we have 2 to the power 3, that is 8, 2 to the power 3 of possibilities. So we are not dealing with a small device, the complicated device. So we need more focus, we need more systematic understanding, right? So but we are not going to, or we I'm not going to discuss all the different eight possibilities, because many of the possibilities doesn't have much utility or application left, right? So we'll have to understand why it is not working, why some reagents are very effective, and what are the different applications. For example, some among this eight, around we use around three to four, other four are obsolete or we are not using. So why that is done and why not that is not done, etc., we'll be discussing. And these eight possibilities are common to both NPN and PNP, right? These eight possibilities are exposed or open to NPN transistor and PNP transistors. Okay, although we don't need to discuss all these different possibilities, let's discuss some few of these possibilities. Now, among these eight possibilities, we'll be basically focusing on three different configurations, right? Three. I only told we'll be discussing three. Although there are four possibilities, but we'll be discussing mainly three different regions. And these regions are nothing but active region, cutoff region, and saturation. Okay, so let's understand. Now we have to connect these two together, different possibility of biasing and different operating regions of a BJT. And in one of this configuration, we have active region, and another configuration we have cutoff, another we have saturation. So we'll discuss what are the different regions. Okay. Okay. So let's start with the active region. We know if a diode, when will be a diode be active? Diode would be active when its p-type junction is higher voltage and than its n-type region. So we call this active. We call forward bias. Forward bias. Forward bias. Forward bias. Okay. So similarly, if I draw the NPN transistor, we know there is a diode in the NPN transistor. Definitely, there is a diode in the NPN transistor. This is diode. So based on this, we can name the transistor. This is P will be N. So definitely this is N. But definitely, if the diode has to work, if the transistor has to work properly, the diode has to conduct some current. But definitely, this should be P should be a higher voltage. That means P should be a higher voltage than this N region, right? So here I need to have a forward bias for the NPN transistor to work properly or to conduct at least. Okay, P has to be plus, N has to be minus, right? This is called forward bias, right? Now, if the diode has to conduct some current or some charge or some carriers, electrons and holes, it has to be supplied. So we need to bias the other region also. That means there should be some supply here. That means I have to provide some charge here. That means current should be sourced here. So I am keeping the collector. And again, I'm writing the junctions here. This is the emitter junction, emitter, and this is the base. This is collector. We'll discuss why these are called emitter, base, and collector soon, right? So we have the emitter and base. Base is the control region, and the collector is the collecting where electrons are collected. Okay, so here we already bias the base and emitter. So base should be positive and emitter should be negative, or we can say less voltage than the base, for that so that it is forward biased. Now the diode has to conduct some electricity or some charge, so I need to supply some electricity here. So I'm just putting positive voltage across the collector also, so that I can push some charge or some minority carriers through this diode. So I keep it plus, right? Now, the question is, what about this junction, collector and emitter junction? Collector and emitter junction, what will be the status of that? So definitely we can see the collector is all right now, it's a positive, a forward bias or a high voltage, but emitter is slightly less voltage than the base region. And in order to push some charge, definitely the collector voltage should be a bit greater or at least equal to the base region. So we can see by default, we can see here there is if what kind of bias is here? Here, yeah, here there is again a forward bias happening here. Not forward bias, there is a bias happening here with collector higher voltage and emitter lower voltage, right? Or you can say in left direction, we can say this direction. In the left side, we can see there's a both plus plus happening. Let's say here there is a plus, here also there is a positive bias. So what about this diode? What happens in this diode operation? Here is also diode. Why I'm calling it diode? Because this is also P, this is also N. So what will be biased there? Okay, so that has to be reverse biased. So what do you mean reverse bias? That means the end region should have a higher voltage here. That means this region has to be reverse bias for proper operation. So why I have told this? Because the collector region has to push some charge. So the end region or end region of this diode, PN diode in the left, which you are seeing, has to be reverse bias. That means the base has to be given lower voltage, the collector has to be given higher voltage, right? Because there's a diode here. You can see the diode here. It's a diode here. I'm drawing it here. So P and N. This is the P and N. This is the diode actually, P and N. So this has to be reverse bias, right? So we are trying to do experimentally analyzing, but if you want to, usually in textbooks and all those, we blindly tell students, yeah, the base emitter has to be forward biased, collector base has to be reverse biased. But here I'm trying to logically explain why I need a forward bias in the base emitter junction and why I need a reverse bias in the base collector junction. Because we have to pump charge to the collector region. So at least that should be greater, that voltage should be greater or equal to base region, right? So let me put in a clear way. Sorry. So we have the end region here, end region here, P region. So definitely NP junction should be forward bias. So this is an end region, so it should forward bias, it should be negative potential. So this I need to give P a positive potential, plus and minus, right? So now the emitter base region has been forward biased. This is emitter region, this is base region, this is collector region of an NPN transistor. Now, what about other junction? The collector base junction that has to be reverse biased. So this P has to be given a negative voltage. This has to be given a positive voltage. So this is reverse bias, right? Why I'm giving reverse bias? I'm telling reverse because N is getting a plus voltage and P is getting a negative voltage in the second junction, base collector junction. And emitter region is getting a negative voltage, is N region, and P is reading a positive voltage, that is P region in this NPN configuration. Now we can say the base emitter configuration is forward bias, this is forward bias, and this is a reverse bias, right? Okay, so by default, we have no, yeah, these two possibilities are there, right? So by default, by applying these two voltage, by default, will get some biasing here. That is, both are end region, so there is not as such biasing right now, but there is a potential across emitter and collector, right? That is, collector region is having a higher voltage than emitter region. So we can say VCE, VCE is here is greater than 0. voltage across collector and greater than zero, something like, okay. So that is also a junction for a voltage point we can measure, okay. But we are giving two biasing in the emitter and collector region, right? So if you reverse the volt setup, we can see, if you reverse the volt setup, we can see the voltage between emitter and collector just reversing. Okay, so that's another region we'll discuss last, but right now you focus on this region. So this kind of setup is for active biasing or active region. Now the transistor say to operate in active region. This is called active region of operation of a BJT. Active region. So simply, what is active region? Active region is that region when a BJT or NPN transistor operates when its emitter based junction is forward biased and a collector based junction is reverse biased, right? So almost all the amplifier applications, we need active biasing or active region, right? So this is a standard in all questions. Someone asks what the region of operation of a transistor while it is operating as an amplifier. It is active region. So what is active region? Emitter based region forward biased and collector based region reverse biased. Now we can see uh, the electrons are entering from which region here? The electrons will be entering to the voltage source, from the voltage source to the end region. Okay, now because it will be attracted to the positive side, it will be going to the P region also. Now P region, it has two options. Either it can divert, go to the battery terminal, or it can go to the collector source. So here there is a decision we are need to make. Electrons has to make a decision. It is entering from the battery. Now it has to decide whether it should go to the positive terminal battery or it should go to the collector terminal of the battery. So although logically speaking, you may think why should go to the collector again? It is actually far away, and again there's an end region in the other side. That is a collector region is actually n type semiconductor. Now most of you may think, yeah, most of the electrons should enter the positive terminal of the battery, right? But although the answer is yes, not all electrons enter this side, right? Electrons are starting from the negative terminal battery, they're entering the emitter terminal, they're passing through the end region, and they're entering the P region, and they have two options right now: either go straight to the collector region or just divert to the battery potential P plus region. Now, although there are some current which passes through the to the battery side, most of the current or most of the carriers will go to the collector region. Now the question is why? The question is why, because your base terminal is very small. The junction or the size or dimension of base is designed in such a way that it is very small, so that majority of the electrons entering the base region will directly go to the collector region. Okay, so this is why we make base very small, so that majority of electrons entering from the base, from the emitter, and also the battery which is negatively biased on the emitter, is majorly going to the collector rather than entering the terminal of the base, right? So that is one reason why we make the base terminals very small. Now that is one reason why we call collector collector collector, because it is designed to collect the electrons coming from the base, right? And that is another reason we make the base region very lightly doped, right? The doping is very high. There is high chance that more electrons can escape into the battery terminals. So we'll make it lightly doped as well as very low dimension size or width, or right. So what happens? All electrons entering the base region will be passing to collector region, major electron majority. Okay. So now I'll write the current. This is the IB. This is IB, base current IB, right? Base current. This is IE, emitter current IE, and this emitter current is diverted to collector as well as to base. So the collector current is IC. Okay, IC. So right now we can see IE is the source. IE is diverted to IC and IB. So I can write an equation, simple equation: emitter current in an NPN transistor equal to IB, some electrons or current flows to the IB region, and some are going to AC. But here you should remember, I have shown the direction of the electrons. I have shown the direction of electron, which is of negative charge. But by convention, we assume the positive flow, the charge flow in the positive holes as the current flow. So, in reality, we have to draw the conventional current like this. This is the IE. IE should be like this conventionally, and IC should be like this, and IB also should be like this, right? So we can see IB and IC are combining together in the base, and they form the IE, right? So IE is equal to IB plus IC still. Even if we see the electrons as negative current, or if we see we'll take into account the whole flow or the positive charge flow, still the current equation doesn't matter. It's only assumption. We are just assuming electrons as negative and holes as positive. That doesn't have any, there is no essential reason. There is no reason behind why we assume electrons as negative and holes as positive. But for our practical purposes, we can reverse also without any problem. Okay, so right now we got equation I equal to IB plus IC, right? So I'll just repeat this whatever discussed again. We have a current flow from the battery, negative terminal of battery, into the emitter terminal, and from the emitter terminal the electrons, it is very highly doped. You should remember, base or emitter region is very highly doped. There's a lot of current flow, and the end region there are a lot of electrons also. This the electrons will be entering in large density in the base region. So when the electrons enter the base region, there are two options. Should either it can exit the base region to the terminal of the battery, or it can go straight. But because of two properties, the base region is very lightly or very small. So most of the electrons doesn't have the time to wait and enter the base region. They just go to the collector region where it is collected. And some electrons enter the base region, and we are intentionally made the base region very low dope area. Very low doping is done in the base region. Okay, so because of these reasons, majority of the electrons entering the base region go to the collector region where it get collects, right? So emitter, it is called so because it emits the charge, and collector is called it collects the charge. And the base is the place where electron has to decide whether it should go towards collector or base. Okay, so we already draw the equations, so we'll just draw the terminal. So this is your transistor, NPN transistor. So we have, this is the base, this is collector, this is emitter. Okay, so the current direction is like this. This is the current direction. This is IE, and this is IB coming from here, and this is IC coming from here. Okay, so just opposite is the action of PNP transistor. Sorry, where the regions of operation will be remaining the same. For example, this is the base, will be remaining base only. Now different base, collector, and emitter. Now the current direction you can say is just opposite. You can say this is IE, which is divided into IB and IC, right? So in both of this transistor, the standard equation of the current is KCL, Kirchhoff current law, is it's IE equal to IC plus IB, IB plus IB. Okay, so this now let's discuss other regions. Right now we have biased the um, emitter based region in a forward bias option, and base collector is a reverse bias option. Now what are the other options? What are the other options? Let's see. Now if we let's see, again, this is the NPN, this is B region. This is the metal connection joint. Okay. Now, if I make the base emitter junction reverse biased, what happens? If I do like this, if I make this reverse biased and here forward bias, just reversing what you have done right now. Now we know if the reverse is happening in the diode, there will be no current flow, right? Because this reverse bias, this what is the meaning of reverse bias? That means I've given voltage. This is plus here and minus here. This is positive in the N side and negative towards the P side. So we can know that uh, all the electrons in the N region will be attracted towards this region. All the holes will be attracted towards the negative of the battery. Okay, so it will be like this. I'm connecting. So I'm connecting a forward positive voltage here and negative voltage here. This is plus, this is minus. So this is a reverse biasing happening in the emitter bias region. So this doesn't allow any current flow in the emitter base diode. Okay. Now let's again connect a forward bias here. So forward bias here means this should be positive plus and this should be negative. This should be connected to the collector. Again we can see that the electrons, it acts forward bias, it will be forcing the electrons into the p region and there may be a current flow here, but still the diode, the thing, it simply act as a simple diode. Transistor action is not here and there is no current in the transistor. There's no current to the emitter current is zero, right? So this region operation where we just uh, sorry in cutoff region, I think. Okay, this has also to be reverse biased. This also has to be reverse biased. This also has to be reverse biased. That means this also has to be reverse. So this should be a positive. This should be negative. So plus and minus. So this is also reverse biased. This is also reverse biased, and this is so reverse bias. So here also there is no current actually because this P region connected to N region, and this P region is connected to negative bias and N region is connected to forward bias plus region. There's no conduction here. So we can say VC, voltage at the point C, is greater than VB. And again, we have VB, voltage at the base. Voltage at the base VB is less than VE. Right? So this happens, there is no conduction in the diode, and this is called cutoff region. So this region is called cutoff region of this cutoff, cutoff region. So we have discussed two regions, cutoff and saturation. Sorry, active region. The other last region is called saturation region. So we'll discuss what is saturation region. So in saturation region, NPN. And saturation region, the condition is we have to bias the base emitter region in forward bias and base collector in again forward bias, right? So how we'll do that? This is forward bias. That means this should be negative. This should be plus. So this is plus and this is minus. Again, the base collector has to be forward bias. So this is again plus. This is again minus. So if this condition exists, it's called saturation region. The transistor state will be in saturation. So here, if we see the voltage magnitude, we know VB. voltage at the base is always greater than voltage at the emitter, right? So this is again, this is emitter, this is base, this is collector. So this is one condition. What is second condition? The voltage at the base here, voltage at the base in this region also greater than voltage at the collector because of the forward bias here. And VP is less than the VE also in the left region also. So in this region, we call the transistors in saturation region operation. Although based on the current magnitude and the internal structure of motion of electrons and holes, we'll discuss in next class how it works, etc. Okay, so we'll stop it here. Any doubts I can clear? Please ask, and you can put your roll number.